Hey everybody, we have a problem coming to us tonight from the Filipino Mathematical Olympiad back in 2008. And a way to rewrite this, we're looking for a value R modulo 7. Sometimes modular arithmetic is referred to as remainder arithmetic, but what we're looking for, obviously this is super large unpronounceable number. We're looking for R being an integer, and it's in the range 0 to 6. And those are the possible remainders. If you divide any number by 7, the only possible remainders would be 0, 1, 2, 3, 4, 5, 6. So R is constrained by this upper bound 6 and this lower bound 0. Okay, so we're trying to reduce this modulo 7 to the smallest value we can. Now, just maybe some examples. 25. Let's see if we can think of a good one. 25 is congruent to what? If you 7 and what does that leave? 4. Yeah, 25 is congruent to 4. And this is just an example, folks. Mod 7. Okay, since 25 is equal to 7 times 3 plus 4. Okay. Now, just to get a grip on the size of this number, the very first sum in here would be 1 to the 7th power. That's easy enough to handle, right? The second one would be 2 to the 7th power. Okay, let's do the customary ellipse to indicate a bunch of stuff we can't possibly write down. This would be 7213, and all by itself, we're going, wow, you know, 7213 raised to the 7th power, right? So obviously, this is a real pain in terms of trying to do a direct computation, but there's a pretty well-known result that we're going to use. You guys may have seen this before. This is called Fermat's theorem. And notice the structure of this. You have a prime here, right here. 7 is a prime. So for any prime, this happens for any prime, not just 7. Another representation would be I to the 6th is congruent to 1. But this formulation of Fermat's theorem is easier. Now, just again, a quick example. Let's see here. 2 to the 7th would be congruent to 2 mod 7, right? Because 7 divides, this divides notation you guys may have seen, divides 2 to the 7th minus 2. And I know that just because I trust Fermat's theorem. Okay, now if you don't trust it, let's see, what is this number? 128. So this number is, so this would be 7 divides 2 to the 7th is 128, right? Minus 2, so 7 divides 126. And that's true, right? 7 is a factor of 126 because 7 times 18. 7 times 18, isn't it, folks? 7 times 18, yes. 7 times 18 equals to 126, okay? And that's just an example of what, of a small number that would work out. And any other number in here, not just a prime, would produce something similar. So what that does for us, if we apply this to the summation, notice how the I to the 7th just becomes I. That's exactly what the statement says. So we've recasted this summation in terms of something that's much easier to manage. Now, this is very well known. This is the triangular numbers where you can find the sum very easily by taking this upper limit and incrementing it, okay? And so that's what we do right here, folks. 7214 divided by 2 is the 3607 you see right here. And so what do we get here? We get S is congruent to, I think, let's see here, 7 times, oh dear, this 7 times 1030, right? 7 times 1,030, that's 7,210, and then we'll put a plus 3 here. Okay. Okay, folks, and again, we're just dividing this by 7 because any multiple of 7 is congruent to 0 mod 7, of course. No remainders of any multiple of 7, right? Now, what about this next one? Oh dear, is that another problem? 7 times something. We know it'll be 500 and something. 7 times 515, and double check that I'm not making mistakes on the arithmetic. 7 times 515 would be 3605, right? So this would be plus 2. Okay. So folks, each of these objects right here, each of these multiples of 7 are congruent to 0 modulo 7, right? Because if you divide an object that's a multiple of 7 by 7, you get a remainder of 0. Okay, so we have congruent to 0 over here also. And so what we get is S is congruent to these remainders multiplied against each other. So S would be congruent to 6. Okay, modulo 7, and that's our answer. The remainder when we divide this guy by 7 is 6. Okay, folks. Again, a lot of work was saved. This is what did it for us right here. You don't have Fermat's little theorem. This result right here called Fermat's little theorem. This would be just an enormous burden to try to reduce this thing. I don't know of any good ways to do it other than just a long, tedious, who knows? I mean, it's a lot of work. I don't know if anybody would want to do that. But anyway, that's it, folks. The remainder is abbreviated here is equal to 6. And y'all, by the way, I just wanted to comment briefly. This PMO, Filipino Math Olympiad national stage, this oral competition, I think it's more of a mental math thing, And so I think the Filipino problem was I raised to the 5th power, and that's much easier to do mental math on I raised to the 5th, right? I did I raised to the 7th, which makes the mental math slightly more daunting, But yeah, I guess you had competitors standing on a stage just thinking about this, answering the questions in front of a lot of people, judges or whatever, I think that's what they mean by oral here. You were just standing on a stage and answering the question. Maybe, I don't know if you had pencil or paper or what, if you're just standing there doing it on the fly and under time constraints, But I think it was the raised to the 5th power here, and that's an easier calculation. Divisibility by 5 is much simpler than divisibility by 7. But in any event, this is, again, a modified version of something that happened back in 2008. So let me circle that, and I'll say good night.